Okay, so action it is. So first we'll go for the proof. So basically, the proof makes use of this Baxter formula, which I gave earlier. And the very first step of the proof, so we're taking this equality. Well, I should have kept it. Let me copy it one more time. So I have f minus t z, which is 1 minus expectation e minus I t. Okay, right? Z to the power tau. Now, under my assumptions tau less than infinity, almost surely I can ignore the event tau less than infinity, and it is equal to exponent minus sum changes from k. K changes from 1 to plus infinity, z to the power k over k, expectation e to the power I t s k s k less than 0. Okay, so that's my starting formula, and what I'm going to do first, I'm going to differentiate both sides of this formula with respect to t. So I will have d over dt f minus tz, and then I'm going to put t equals to 0. Okay, so that's a standard thing. So I have here, well, almost a characteristic function. So if z was equal to 1, I would have a characteristic function. If I want to find the mean of chi, of course, I differentiate the characteristic function. This should give me the mean. Okay, so that's what I'm doing now. So when we differentiate the right-hand side, so what we are going to get is the sum from 1 to plus infinity, z to the power k over k. So that there was no t here, and the only t which I have is inside the expectation. So when I differentiate this, I will get I times xk, so that's going to be expectation, sk, on the event sk less than 0, e to the power I times, I'm going to put t to be equal to 0, so that's going to be 0 sk. So you can simply ignore this exponent, and I will multiply it by exponent minus the sum from 1 to plus infinity, z to the power k over k. Now here, when I put t to 0, I will have 1, and as a result I will have expectation of 1 on the event sk less than 0, which is going to give me probability that sk less than 0. Okay, so probability sk less than 0. That's the product of those. Expression, so I think I can simply erase this exponent and get expectation sk less than 0. Well, and on the left-hand side, I'm going to get, so this one will disappear, and when I differentiate exponent, I will have minus I expectation minus I times chi, and then expectation I 0 chi z to the power tau. Okay, so that's my left hand side. Okay, now what you can see is that first of all I can cancel my imaginary number I from the left and the right hand side. Okay, and also I can erase one of the matrices. So that's my resultant expression. You know, before doing anything else, I need to analyze this term. Okay, so now minus expectation of sk less than 0. Okay, so what I want to do now, I want to find the asymptotics of this term. Okay, and this asymptotic is something which I'm going to use. So what I have is expectation of modulus sk less than 0, which I can write using one of the formulas for the expectation as the integral from 0 to plus infinity probability that sk less than minus z is
Z better not to use, no?
Yes, I agree. Let's use y. Scale less than minus y dy. Okay, so I hope this formula is clear. Okay, so that's what I have now. I want to apply the central limit theorem here, and for that I just need to rescale from. Okay, so let's do the following rescaling. So I'm gonna introduce new variable u, which is equal to y divided by square root of k. Okay, so that's my new variable. Then this integral is going to be square root of k, integral from 0 to plus infinity, probability as k over square root of k less than minus u du. Well, and then I'll just apply the central limit theorem, right? So my random walk sk has 0 mean, has finite variance, so the central limit theorem is applicable. So this integral should converge to the integral from 0 to plus infinity, probability that z less than minus u du, where z follows standard normal distribution. Okay, so this integral is actually not difficult to find. Okay, so I can write it. So I'm going to use this blackboard. So integral from 0 to plus infinity, probability that z less than minus u du. This is nothing else but expectation of z minus, right? So that's you take in the negative part of the standard normal distribution, that's your expectation, which is integral from 0 to plus infinity, 1 of the square root of 2 pi u e minus u squared over 2 du. Now, well, this is something which is integrable, and as a result I'm going to get 1 of the square root of 2 pi. So after I perform my integration. Okay, so after I've done this computation, so it means that when k increases, this integral will be approaching that number, and as a result, this coefficient, expectation minus expectation sk less than 0, is going to increase as a square root of k times 1 over square root of 2 pi as k goes to infinity. Are you familiar with this notation? If you divide left and right hand side, it should converge to the same unit. K goes to infinity. Right, so that's so this is the result of my computation. So now let's just...
So for this integral converging, are you sneakily using Virial's theorem?
Well, you mean for this
expectation switch?
for this representation?
No, the fact that the integral converges because the integrand converges.
Right, so let me think.
So I think if you write the probability of the expectation of an indicator, I guess you can use...
Well, if you swap, then you're going to get probably the same thing as in the beginning.
It's just the same formula.
Yes. So Virial theorem is how you get from expectation to this formula.
So using dominated conversions?
Yeah, I think so. So here, wait a second. So it's
No, there are several ways to prove it. You can use quantile functions, you can use whatever you want.
I'm prepared to believe the result.
Yeah, we do it in second year. Actually.
Are you sure?
Yep, I used to do it in second year.
Well, I thought you did in the kindergarten. You say.
Yes, but for my students I do in second year.
Oh,
I did this in the word.
In the kindergarten I was doing something else, you know?
That's fine.
well, at least it's believable for me.
Yeah.
So let's agree on this. Okay. So okay. So let me just rewrite it one more time. So we have these asymptotics. Now what it means that if we put, if we denote this as qk, so qk is minus 1 over k, expectation as k less than 0, then this qk will behave as 1 over the square root of 2 pi times k, when k goes to plus infinity. So now I can erase these computations. That's the main thing which I need. So my question is, I have this information about qk, right? So qk behaves like 1 of the square root of k. And I have this series, k changes from 1 to plus infinity, z to the power k, qk. So eventually, when I look at the left-hand side, so I want to get rid of z as well. So to get rid of z, I should let z to be equal to 1. So if I just put z to be equal to 1 here, I'm going to have a problem, right? Because qk behaves like 1 of the square root of k. So my series is going to diverge. Okay, so directly it doesn't work, but what I can do instead, so I can, so hence, I will consider the limit. As z goes to 1, so the limit of this series, how it behaves, and for that I need another powerful result, which is called the Virial Theorem. And I'm going to put this result on the blackboard. So this is a statement in two directions. So this is called the Virial Theorem. So I'll call it probably theorem T, because well I'm gonna make use of this theorem, but I'm not going to prove it. So suppose we have a series of these forms. So let Q greater or equal than 0, and we have this series Q of Z is equal to the sum over and changing from 0 to plus infinity Q n to the power Q n Z to the power n. And we assume that this series converges for 0 less or equal than z less than 1. So the radius of convergence, well, I'm not talking about radius of convergence here. Okay, so the series is convergent. Now, well, I'm going to state probably a more general form of this theorem, but we will use it in a singular form. So if L is a slowly varying function, well, I don't know if you know what the slowly varying function means, but what I can say is that constant is a slowly varying function, and we're gonna apply this theorem with L being a constant. Okay, so the theorem is applicable. So if L varies slowly at infinity, whatever it means, and 0 is less or equal than t, less than plus infinity, then Q of z asymptotically behaves like 1 over 1 minus z to the power p, L 1 minus z, if and only if the sum Q0 plus Q n minus 1 behaves like 1 over gamma, so e plus 1, n to the power p, L of n. Okay, so, well, So this is already sufficient for me, but I'm going to use this theorem one more time later on. So I will add this extra statement. So if Qn, if in addition Qn is monotone, and 0 less than p less than infinity, then Qn behaves like 1 over gamma of p n to the power p minus 1 of n. So that's the second statement. I'm going to be needed later on. So now I'm going to use the first statement. Okay, so how am I using the first statement? So I want to say something about the behavior of these power series as z goes to 1. Did I say it anywhere? So here z goes to 1. So symptotics when z goes to 1. So this is symptotics, and this is symptotics is when n goes to plus infinity. Right? So basically, if what this theorem says, if we know how the sum of q's behave, if it behaves according to this rule, then you can make a statement about q of z. So let's find how the sum of q's is behaving. So q naught plus qn minus 1 behaves. I know that this series is diverging, so therefore I can just substitute this symptotics to find the behavior of this series. That's going to be the sum from 1 to, well, you can put n 1 over square root of k 1 over square root of 2 pi. Okay, so that's my series. Now, the symptotics of this series is not hard to find, so that's the same as the symptotics of the integral, right? So if you replace, that's the same as 1 over the square root of 2 pi, integrals from 1 to n, dy over square root of y, and then, now this is the same as, let me, 2 divided by square root of 2 pi n to the power 1 over 2. Okay, so that's the symptotics for my sum. So now I just need to recognize the terms. So I want to apply this theorem. So first of all, in this theorem, p is equal to 1 over 2. Okay, so I n to the power p, so p, I'm going to take p to be equal to 1 over 2. So now I should have 1 over gamma 3 over 2 in the denominator. So basically 2 over square root of 2 pi is equal to L of n divided by gamma of 3 over 2. Now you can find the value of L of n. So L of n is a constant. So we should take in this theorem L of n to be equal to gamma 3 over 2 times 2 divided by square root of 2 pi. Now I just need to recall what gamma 3 over 2 is. First you use this rule, so that's 1 over 2 gamma 1 over 2, right? Times 2 over square root of 2 pi. So this 2 and that 2 are going to cancel each other, and then I will have square root of pi, so gamma of 1 over 2 square root of pi, divided by square root of 2 pi, which is just 1 over square root of 2. Okay, so that's my L of n. So now, once I have all those coefficients, so indeed, this is satisfied. I found this asymptotics with this constant, with p equals 1 over 2. Now I can say that Q of z is going to behave. So by theorem T, Q of z is equivalent to 1 over 1 minus z to the power 1 over 2 times L of 1 minus z, but this is just 1 of the square root of 2, right? So that's a constant.
Maybe. Denis, if you could write a bit higher, not in the last 30 centimeters,
Okay.
so the people from the back would be better positioned.
Yeah, try so I don't think I'm gonna need. Yes. Okay, so just let me repeat. So by theorem, my theorem T, Q of z behaves like R1 divided by 1 minus z to the power 1 over 2 times 1 over square root of 2 as z approaches 1. Okay, so that's what we need. So now what I'm gonna do, I'm gonna replace this by Q of z because this Q of z. I don't think I need this anymore. I'm almost done. Okay, so here I have 0, so I can erase this bit as well. Okay, so that's my equality. So now, as z approaches 1, so what happens here? So the left-hand side is going to approach expectation of chi, right? So expectation of this overshoot. We don't know yet whether this is finite or not. So still, we have to do this, but it's quite close. So that's the left-hand side. But because chi is a positive, non-negative random variable, we know that it exists. So it might be finite, might be infinite, but for sure we know that it exists. So the left-hand side is expectation of chi. Now on the right-hand side, what we know is that Q of z behaves like 1 over the square root of 2, 1 divided by 1 minus z, 1 over to the power 1 over 2 times expectation minus the sum from 1 to plus infinity z k over k probability as k less than 0. So now we have a much nicer expression. So it was ugly, but now it's almost what we want. So now what I'm going to do now is I'm going to represent this ratio as the exponent. So this is equal to 1 over the square root of 2 exponent minus 1 over 2 logarithm 1 minus z. So this is my ratio. Okay, so that's just the usual rule. And here I will combine this term. The sum from 1 to plus infinity z to the power k over k probability that s k less than 0. Okay, so that's the first simplification. Now the second simplification, I'm gonna use the Taylor series of logarithm, right? So what we know is that this logarithm 1 minus z is nothing else but the sum of z to the power k over k with minus. So this is equal to 1 over the square root of 2. Okay, so I'm gonna erase this bit, that bit. And continue here. So that's going to be 1 over the square root of 2 exponent 1 over 2, the sum k changes from 1 to plus infinity, z k over k minus the sum k changes from 1 to plus infinity, z k over k, probability that sk less than 0. And after all, we can combine those two series together. So that's 1 over the square root of 2 exponent minus the sum k changes from 1 to plus infinity, z to the power k over k, probability that sk less than 0 minus 1 over 2. And this is almost what we want, right? So that so I can now erase those things. Okay, so that's my equalities, expectation of as that goes to 1, behaves like this. Now we can argue by contradiction. Now there are only two possibilities. When z approaches to infinity, to 1, sorry, this series converges to a finite number, then we are fine. That's what we want to prove. So this series is finite, and then expectation of chi is finite, and it's going to be equal to 1 to the square root of 2 e to the power of this sum, as required. Okay, so we are done. Now, if this series is not finite but infinite, then we will have the following contradictions. So suppose this series is infinite. Suppose that the sum from 1 to plus infinity, 1 over k, probability s, so zk, probability sk less than 0 minus 1 over 2, z to the power k, converges to plus infinity as z is a plus, so it should converge to minus infinity, right? Converges to minus infinity as z approaches 1.
Why?
Huh?
Why?
We need to check this.
No, why should it converge to minus, not plus? Why?
Well, there's a suppose in front.
No.
So if it converges to plus infinity, so what will happen is that we're going to have e to the power minus infinity, which is 0. Now this will imply that expectation of a positive random variable is equal to 0, and this random variable will be equal to 0. But somehow, if you recall the definition, then the definition says that this is the value of the overshoot strictly below 0, so it should be strictly greater than 0. So this case is included immediately. Okay,
And
so
it cannot oscillate because there should be monotonicity. Right?
Who connected us to it?
With the
This
sum as-
expression, when z goes to 1, how do you know it converges either to plus to minus infinity? It cannot oscillate, right? Why?
Well, on the left-hand side we have a number, right? So
It should converge.
it should be a number. Yes, so it should be some
Okay.
number. So it's
Mhm.
0, positive number, or
So it is either finite number or infinity, that's all.
yes.
Yes.
Yeah. So finite number we are happy. If it's infinity, we are not. If it's minus infinity, we are not happy yet. But what will happen is that basically, so this computation was about expectation of I. So expectation of I is going to be equal to plus infinity if this is true. Now what we can do, we can repeat the same computation, but for expectation of the chi plus, which is the overshoot in the positive direction. So in this case we're going to get exactly the same formula, but so that's going to be lim z goes to 1 the square root of 2, expectation, exponents are minus the sum from 1 to plus infinity, z to the power k over k, probability that sk greater than 0 minus 1 over 2. Okay, so that's going to be expectation of chi plus. Now, what happens is that if you now, so this sum is minus infinity. So now, if you add those things together, what you will get is probability that sk is equal to 0. Okay, so if we add those two terms together, so adding the sums, we just a second, so is the sum correct? Is the sum correct? We obtain. So if we add this term and that term, we'll get probability sk less than 0 plus probability sk greater than 0 minus 1. Yeah, right? So what will be left is just probability sk equals 0. And we will obtain the sum from 1 to plus infinity z k over k probability that sk is
With a minus sign.
equal to 0. Well, it doesn't matter what this is. Now, what matters is that when z approaches 1, so have probability sk equals to 0, but this probability implies concentration inequalities. Or well, you can use local theorem as well if you wish. So this probability sk equals 0 is less or equal than c over square root of k. So effectively what happens is that you have, when z approaches to 1, you have 1 over k to the power of 3 over 2. This is always finite. Okay, so the conclusion is that this sum plus that sum is going to be something finite. Now this sum is minus infinity, therefore this sum inside is going to be equal to plus infinity, and you end up with e to the power minus infinity, which will give you 0 here. Okay, so that's again not possible. Okay, so less than infinity, so then expectation of chi plus will be equal to 0, not possible. Okay, so the only reasonable thing to happen is that this converges to some finite number which we call C, and then we're going to get the statement of our theorem. Okay, so this is done. So that's the hardest part of the proof actually, the fact that this sum is finite. Now, so I can erase it, right? Okay, so let me. So how much time?
10 minutes,
10 minutes.
maybe 15.
Maybe 15. Okay, so that's good because I think I should be able to prove the second theorem. Okay, so let me summarize. What we did, we proved that expectation of Sn, expectation of chi is finite under this assumption, and we obtained some expression for this expectation, which I'm going to use. So I'm going to copy this expression. So that's equal to 1 of the square root of 2 exponent. The sum k changes from 1 to plus infinity. Probability that sk less than 0 minus 1 over 2 with my history. Okay, so that's my expression.
Shouldn't there be some k's?
There should be some k in it. Should have 1 over k. Okay, so let me just check. Okay, so that's the hardest part, as usual. So expectation of the overshoot is the hardest part. Now we will use this expectation actually to find asymptotics. So we are now ready to find asymptotics. Now to find asymptotics, for probability tau greater than n, put t to 0. So we put t to 0 in the Baxter-Spitzer identity to obtain Spitzer identity. So in the Baxter identity, let's write it down. So what we will get then, 1 minus expectation of z to the power tau is equal to exponent minus the sum from 1 to plus infinity z to the power k over k, probability that sk less than 0. Okay, so this has a much neater form. So this identity which I have now. Now, if you compare what I have here with this expression, it looks like a good idea to subtract 1 over 2 here. Right? If I subtract 1 over 2, I'm going to get something like this. Okay, so let's do this. So I will here exponent minus the sum from 1 to plus infinity z to the power k over k probability as k less than 0 minus 1 over 2, and of course if we subtract something, we need to add this back, so I will have exponent minus 1 over 2, the sum from 1 to plus infinity, z to the power k over k. Okay, so I'm just changing the right hand side. Nothing is going on here yet. Okay, and again, so we have already seen these exponents, so this is just 1 over 2 log 1 minus z. Okay, and the exponent of 1 over 2 log 1 minus z is going to give me 1 minus z to the power of 1 over 2. So I can write the third equality as follows. That's going to be exponent minus the sum from 1 to plus infinity z to the power k over k probability s k less than 0 minus 1 over 2 times square root of 1 minus z. Okay, and well, let's copy this. It is 1 minus expectation z to the power tau. Okay, so one more transformation. Now let's divide. So now it might look like some kind of magic, but you will see shortly why I am doing all those things. So let's divide both left and right hand side by 1 minus z. Okay, so we divide by 1 minus z, so then we're going to get minus expectation z to the power tau divided by 1 minus z on the left hand side, and this is something which I want to transform. So let's transform this bit, and well, on the right hand side, well, we're just gonna get exponent times 1 minus z to the power minus 1 over 2. Nothing's really going on here. So let's do some transformation. So first of all, what I have here, so I have I know that my random variable is a proper random variable, so the sum of probabilities that tau is equal to n is going to give me 1. Okay, so I'm just replacing 1 by this sum. And here I'm going to write down the definition of expectation. So I have z to the power n probability tau is equal to n, and everything is divided by 1 minus z. So if I combine those things together, I will get the sum from 1 to plus infinity 1 minus z to the power of n divided by 1 minus z, probability that tau is equal to n. Okay, now, well, you can recognize that's the sum of finite number of geometric series. So, I have the sum from 1 to plus infinity, and here I will have the sum changes from 0 to n minus 1 z to the power j. So that's what my ratio is. Probability that tau is equal to n. Now, once you have two summations, the first thing that you need to try to do is just to swap them. Okay, so that's what I'm going to do. So I will have the sum of j changes from 0 to plus infinity z to the power j, and this summation will go inside. So the sum n changes. So n is always greater than j, so n changes from j plus 1 to plus infinity, probability tau being equal to n. Well, after all, I will get the sum j changes from 0 to plus infinity, z to the power j, probability that tau greater than j, up. Okay, so which I'm going to copy this sum on the left hand side, and I'm going to replace j by n. So on the left hand side I'm going to get the sum from 0 to plus infinity, z to the power n, probability that tau be greater than n. And on the right hand side I have 1 minus z, but I will square root 1 minus z, but because I was dividing by 1 minus z, I will have 1 minus z to the power minus 1 over 2. Okay, so that's my expression, and this is the expression which I can analyze now. Now what happens is that I'm going to use this Virial theorem one more time. Okay, so now let z go to 1. So the nicest thing is going to happen here, because when z approaches 1, we have just shown that this will converge to expectation of the overshoot. Okay, so this will converge to expectation of the overshoot. So the right hand side behaves like expectation of chi times 1 minus z minus 1 over 2. Okay, so this is my right hand side, and this is my q of z.
The square root 2.
Yes, I should put square root of 2. Indeed. Okay, so on the left hand side I have q of z, on the right hand side I have this expression. Now if we go back to this whiteboard, so what do we have? So we have q of z behaving like this. Now we do have 1 minus z to the power minus 1 over 2. So if we take p to be equal to 1 over 2, it looks like that's exactly this form. So we take p equals 1 over 2, and also, well, as usual, L is just a constant, and L is going to be equal to square root of 2 expectation of my overshoot. Okay, so that's the right hand side. Now the theorem says, well, all conditions are met, so these are positive Qm, so these are Qm, so these are greater or equal than 0. So the theorem will allow me to say something about the sum of Qm, but now we can use this additional statement. Qm is a monotone sequence, so probability that tau greater than n is monotone decreasing probability. So what we can conclude from this theorem is that probability that tau greater than n behaves like 1 divided by gamma of p, gamma 1 over 2, times n to the power p minus 1 is going to be n minus 1 over 2, and the constant is square root of 2 expectation. Okay, sorry. And well, let me just simplify. So that's going to be square root of 2 over pi expectation of chi divided by square root of n as n goes plus infinity. Okay, and that's the result which I wanted to prove. So what we have done is, so we found asymptotics for probability tau greater than n as n goes to infinity. So basically using the Baxter formula. Baxter formula is just follows from the Wiener-Hall factorization, and that's a very classical approach to this problem. Okay, so this is not done yet. Yeah, so just a few words about what's going to be next time. So we found these asymptotics for tau greater than n when we start at 0. So next time I will start by showing that you can use these asymptotics to quickly derive asymptotics for start from arbitrary point of time. So the random walk might start at arbitrary point of time, and then you're going to get something similar, and that's when the renewal function will appear. Okay, and then I will discuss how you construct conditional random blocks using this classical approach. Okay, so I'll stop at this point and well, see you in a week.
Thank you.